Hello and welcome to this webinar, Flow Optimization of an Intake Manifold using Generative Design. I'm your host for the webinar today. I'm Reshmaa Selvakumar and I'm the Application Engineer at Diabatix. As part of today's webinar, I will walk you through the process of setting up a flow optimization case on our ColdStream platform. Of course, for this example, I've chosen to work with an intake manifold, and that's the case that we will be seeing today. We will walk through the entire process of a case setup. We will look at some of the constraints and objectives, and we will also look at the post-processing of such a case. If you have any questions, please feel free to let them out in the chat box. I will look at them and answer it at the end of the session. But without further ado, let's get started. To start with, I want to give you an outline of how this webinar is going to progress. We're going to start with the workflow, and the first thing that we will do is a CFD simulation. And what I want to do with the CFD simulation is just show you how simple it is to set up a simulation on the ColdStream platform and what that entails for you. After that, we will look at a design case. So that's what I mean by case setup. So we will look at how to set up an optimization case on the platform. And after that, we will look at the post-processing of the same case that we set up. So this is just to show you how everything works on the ColdStream platform. Let's start with the simulation first. I'm logging onto the platform and we should move to ColdStream so I can show you how simple a CFD simulation is on the ColdStream platform. Okay, now we're on the ColdStream platform. Let's start with the simulation. I'm just going to add case now. For this particular simulation, I went with a very classic, simple example of a bended tube, and I wanted to show you how you would run a CFD simulation on that. Now, typically for any simulation on any of your classic CFD tools, you would start with uploading or loading your geometry into the software, which is also something that we do on our platform. You start with a step file and you will have to upload it. So once you have the step file, you populate the case. Okay, now that you've loaded the geometry onto the platform, typically in a CFD tool, you'll have to clean up the geometry, which is not something you have to do on our platform at all because you're just uploading this from your CAD tool as a step file, and that's it. You don't have to clean it up over here. And then after that, what you would typically do is take care of meshing, and then you would include all your setup, and you would typically end up having at least especially if you're not an expert at CFD, you would have some kind of meshing issues and you'll have to spend 3 or 4 days fixing the meshing issues, and then you will start the case setup. But in our case, you don't have to bother about the mesh at all. We have quite an advanced meshing tool, so it's not something that you have to be concerned about. It's all automated for you, so we can move to the point where we start the case setup. Now, to start the case setup, as you can see here, we have one region, which is of course the fluid region, and two boundaries, and that is basically your inlet and your outlet. So let's say your inlet's here and your outlet's here. You can also visualize it here on the platform, and you just start setting up the case over here. So the region type would be fluid, and then I would give fluid region. That's the name that I'm going for, and then I can select a material. Now the material itself can be any kind of fluid. You're not limited to using only water or only air or oil or whatever. You can use whatever fluid material or that works for you. So we just set it up with the appropriate material that works for it, and then we can choose the relevant settings. So typically you also have to make a choice on the turbulence model, but that is not something that you have to concern with on our platform. You can simply let it be with K omega SSD, which is our default setting. But if you want to make a choice, then you do have the option to make a choice of the turbulence model as well. Other than that, if you're setting up buoyancy or radiation, they will play a factor. But of course, this is a CFD, simple CFD solution. We are going to set it up without any buoyancy or radiation in it. The next thing, classically in any of your CFD tools, other than the turbulence models, you'll have to also think about other boundary conditions, your Y plus values, and all of these complex mathematical, you know, solutions that you have to think about, but you don't have to bother with any of them in the platform. Most of it is all automated. The only thing that I'm going to do for the simulation right now is set up the kind of boundary or the kind of inlet and outlet that will work for this case. I'm going to go with a very classic case, and I'm going to go with the fixed flow rate inlet. I'm just going to call it an inlet, and then I will give the inlet temperature of the fluid. So let's say the inlet temperature of the fluid is around 300 Kelvin. And I would include a volumetric flow rate or a mass flow rate because it's a fixed flow rate. So for a volumetric flow rate, I'm going to go with somewhere around 0.15 meter cube per second. And then, of course, you'll set up the outlet. So I'm going to go with a very classic pressure outlet solution. So outlet, and at the outlet, I'm keeping the pressure at 0. And that's it. That's all you have to bother about on the platform. That's how simple setting up a simulation on the platform is. You would validate the geometry, submit the case, and forget about it. And you have time while the software runs to think about other things and put your time into more more valuable tasks at hand rather than worry about one simulation for 5 days. So we could just submit the case, say conceptual for 15 credits, and it runs in a day, and then you have the solution in your hand. So you can take the time to look at something else. Okay, now that the CFD simulation is over, just to bring you back to the workflow, the next thing we're going to look at is the design case. Like I said, the CFD simulation is so simple that you can just set it up and let it run, and you can use all your extra time to really think or put it into things that are of more value, like how to improve a design and the optimization of a design for your cases. So that's also what we will do today. And just before I take you back to ColdStream, I wanted to show you a little bit about the case itself. So this is a simple flow optimization case, and because it is such, this is how the assembly looks. I have set it up as well as a very simple case. And you will see quite a few similarities between your CFD simulation and your design case setup. But yeah, it's still a slightly different case setup because you will include a geometry or a design region in this particular case. So the first region that we have is the fluid region. You have an inlet indicated over here and 4 outlets. And this is the fluid that we're looking at. It's air. It's a simple fluid region, and we will include these boundary conditions on the ColdStream platform. The next region, it's a single region problem in this case. It's a sub-region. This region is part of the flow region, and this is your design region. This is specifically where you want your structures or channels to be drawn by the software. What we're going to do today in terms of an optimization target is that we will do a power dissipation minimization with the velocity variance constraint. A power dissipation minimization is because we want to reduce the viscous and pressure losses in this problem, and the velocity variance constraint will set in the outlets to ensure or to set a constraint of ensuring uniform flow at the outlet. So that's what we're going to do. Let's move to ColdStream. Now we are on the ColdStream platform. We will start with setting up this case. So let's go to the project and then add case. For optimization. You have two choices on case type. One is a design case and the other is a simulation. A design case is really your optimization case, whereas your simulation would be a CFD simulation, which is why in this particular case, I went for a design case type. So we start setup. To start with, we have to upload a step file. So this is our geometry step. The platform currently only handles step files. So you have to make sure that the geometry that you're uploading or the CAD file that you're uploading is a step file, and in particular is a part step file and not an assembly step file. I'm going to upload the step file now. You can, of course, so in this case right now, what I'm going to do is upload a single step file that has all the different regions and boundaries all together. But you can choose to do it differently. You can include it as separate regions and separate boundaries, and you can add them as individual step files as well. It's really up to you how you choose to upload them. All right, so now we have the geometry uploaded. It's a very simple case and we can just quickly set it up right here. So as you can see here, there's only one region, which is our fluid region. There's a sub-region, which is our design region, and 5 boundaries, so 1 inlet and 4 outlets. Let's start with setting up the region first. So we click on region 0, and then we can choose the region type basically. Here we will choose fluid. We can give it a name. And then we can select a material from the library. Now, in this case, I have a pre-written or a preset material that will work for this case. But if you have a material that you want to include, you can just include it in our libraries page. So there are no buoyancy related settings that apply here, nor radiation. So I'm just going to leave it as is. And in terms of the turbulence model as well, I will leave it with K omega SST. So the region settings are done. Now I can set up the boundaries first. So just to give you an idea of which is the inlet and outlet, we should take a look at it. So this would be our inlet, and these 4 sections here would be our outlets. So let's start with setting up the inlet. So that's boundary 0. It's a fixed flow rate inlet. We give it a name. And then we include the temperature and the mass flow rate. So in this case, the inlet temperature is around 20 degrees Celsius, so 293.15 Kelvin. And then we also have a mass flow rate of 0.048. that's it for the fixed flow rate inlet. There are no other boundary conditions for here, so we can end this. The next are the outlets. So here right now what I have done is I have of course included each outlet as a separate boundary, but you can also include all these outlets as one boundary. So you can include that as just one step file, so you don't have to set this up individually like I'm doing, which I highly recommend for you to do when you have more fancy or like complex cases with a lot of different regions and boundaries. It's really hard to keep track if you have about 16 of these or 25 of these. Then I do recommend you can set bunch them up together and set them up as well. As long as they don't directly affect your optimization process by doing so, I do encourage you to do that just to make sure, just to make things easier, and also to make sure that you're not making any mistakes. So this is just a standard pressure outlet that we're going for, and we're just naming them as well. Oh, sorry, outlet 3, and then outlet. All right, so the boundary conditions are done. Now we can start discussing the design region. All right. So in the subregion type, you can choose between a general subregion or a design subregion. In this case, it's the design subregion, so that's what we will make a choice on, naming it design. And then we select a material. So right now, what we've had so far is, of course, a fluid region, but here this will be solid. So I'm going to choose an aluminum alloy, which is the same material as my solid for this case. And I'm choosing that as my material for my design region. The next thing, which is the most important part. So now we've finished 3 steps. We've included the geometry, we've included all the boundary conditions, and a design region. The next step is, of course, to include the manufacturing constraints and settings. So we start with choosing a manufacturing type, in this case 3D printing, and then we choose the relevant manufacturing settings. So I've already filled in some manufacturing settings. I'm going for 3D printing, but with a 1 mm feature size, and that's what I'm choosing over here. If you have other manufacturing types, you can choose them, and then of course, make sure to include your most relevant manufacturing settings for that particular manufacturing type. So at this point, everything for your case setup is done. You're only left with setting up your objectives and your constraints. So I do want to walk you through this a little bit more in detail. That is about the constraint and the constraint and the objectives that we are setting. So what we are going to do right now is we're going to set up the constraint, we're going to set up the objective, and then take a look in detail about this objective and constraint. So starting with the constraint, we are going to set a velocity variance constraint on all the outlets. So you click on add target, and then you choose the velocity variance constraint. Now, the difference here is if I choose velocity variance minimization, that is an objective. Whereas when I choose velocity variance, that is a constraint. So there are 2 kinds of targets that are available, an objective or a constraint. And based on your case, you have to make the right choice. My target value over here is 1250. And I will repeat this for all 4 of my outlets. So like I mentioned earlier, this is why I recommend that you include this when you have 4 or 5 outlets of 4 or 5 of the same feature, that you include them as the same surface setup when you upload your geometry, is because it's easier to set up the case like this. You don't have to keep repeating the same target and then double checking if the constraint has been included all the time, because if I'd included all four of them as one boundary, then I would have only had to set it up once. So it's just to point out small tips and tricks that can make it easier for you on the ColdStream platform. So we've set all of these outlets with the velocity variance constraint. Now for the objective. The objective that we're going for is a power dissipation minimization. It's very similar to a pressure loss minimization, but this is a power dissipation minimization objective that we will set up. And then we will look into this a little bit more in detail as well. So the case setup is done. As you can see, I have green check marks over here indicating that I have completed the setup of all these regions, subregions, and boundaries. I'm going to validate my geometry and then I will submit the case. Of course, it's important to note that all these steps have been carried through during this case setup. So we uploaded a geometry, included the boundary conditions, a design region, then the manufacturing type and the relevant settings for it, and lastly the optimization targets that we're going for. Once the geometry is validated, we can submit the case. Now, when you click on submit, you have two options. It can either be a detailed case or it can be a conceptual case. Now, your detailed case is when you want the most accurate results as well as a high resolution manufacturable design. A conceptual is really a first estimation of how your results would look. And they're also really good if you're not sure of your parameters and if you're still experimenting with what value to go for, or what what inlet or what outlet to have. And it's just a good testing situation before you freeze all your input parameters and then go for a more detailed design. A conceptual is not manufacturable. And of course, because of that, because it's a lower resolution computation, it takes a shorter amount of time compared to your detailed. So to submit a case, you will need credits, and the choice of credits will be based on how much you have on your credit wallet. The standard procedure for any design case is anywhere between 85 and 100 credits. And the credits are how we estimate, or we arrange certain computational resources for you to use. And this is set aside for your use during the period that you have the license. So I'm just going to run a detailed case for 85 credits. And then your case has been set up. We've done a CFD simulation. We've also done a design optimization case setup. Now let's take a look at the post-processing on the ColdStream platform. I've taken the liberty to run the same case a month ago so that I have results available to show you on this webinar. So this is just the same case that was run previously, so we don't have to wait to see the results. When a simulation or a design case is finished, you will receive a notification on your email saying that your case has been completed, and you will be able to take a look at the finished results on the platform. So when you click on a finished case, this is the first page that you see, which is a case summary of the different parameters that you can have a quick glance on, like temperature, pressure drop, flow rates, etc. You can also change the units and visualize these parameter or results of these parameters in the units that you like. Another thing to mention here is this is also how we transfer results to you. So you will be able to download the results as well as the design by clicking on these tabs over here. The results is really something that you can post-process on your post-processing tool and take a much closer look at these results. The design, on the other hand, would be a step file that you get of the design of the case that you run, and you'd be able to take a look at these features more closely. On the other hand, by clicking on the Case 3D Results tab, you will also be able to visualize these results on the platform and do some or take a look at some basic post-processing here itself. All right, so let's take a look at this design. Okay, I'm going to start with showing you the design features along with the streamlines. So this is basically the additional material or how the design has been modified for this manifold case. I understand, well, this looks quite fancy. You cannot quite tell how the flow is going. So there are two ways that we can take a look at the flow itself. So either I can show you the fluid region or the streamlines. So I'm going to start with the streamlines, and then I will also give you a very good view of the fluid itself. Just going to change the color of the streamlines. Well, I can just give it a solid color to take a look at just the streamlines, but I'd also like to do it with velocity, just to take a look at how these streamlines look. So this is how the design looks, and this is also how the fluid seems to flow in this case. So you have the big outlet here, this part that is blocked, and then you have it reaching these four outlets at this end. Well, this looks like it's, quite an untangible design in the sense of you have these random features up here and here, but it does make sense, and I will show you a better view. So I'm just going to remove the design plot and show you the fluid. So this is how the fluid is, and like I said, this is the inlet, this part is blocked, and then you have the four outlets over here. Now, if you look at how the optimizer has modeled it, and we move behind, we see all these big chunks of material that is added, especially this really weird lump at the back over here that is pushing towards this particular outlet. And while it looks quite abnormal, but when you think about it, there is no other way for us to push the flow all the way towards that outlet and still maintain quite a uniform velocity on all four of these outlets. So the software has deemed it necessary to include this larger bulk or bulky solid at this end to reach this outlet over here. And that's what you see here in the design as well, as opposed to for all the others you have quite a straightforward, in a certain sense, flow path. So for example, for this outlet, you see that your inlet starts and then you just reach it quite in a more straightforward path. But to reach this outlet, what has been done here by the software is really to split the flow at the inlet level, push it back, and then bring it towards the outlet, which seems to give you a better result in terms of getting a uniform velocity or flow rate at these outlets at the same time. So these are certain choices that the optimizer makes to still meet or modify your design to meet your constraints and objectives. So this is how the design looks, and this is how the manifold would look as well um, for you. It's pretty cool. Yeah, so like I said, you can play around with some post-processing here. You can take a look at these surface plots with different parameters as well, so you can color it. Oh, yes, Now, with that, we come to the end of this webinar. As promised, I'm going to take a look at some of the questions that have been sent across on the chat box. Let's see. Um, okay, so the first question is about the mesh. It asks, can I change the mesh? Can I import a mesh from another software? There is no direct way that we can influence the mesh resolution on our platform, because your choice between a high resolution and a low resolution is really the kind of design that you would want to do. So whether it's a conceptual design or a detailed design, um, you cannot import a mesh from another software, because right now we have or at the on our software we have a very good advanced meshing software. It directly automates everything, so you don't have to worry about any of these parameters at all. You can just set up the boundary condition, set up the simple case setup, and you're done. You don't have to worry about the mesh. So no, you cannot change the mesh or import it from another software, because it's all automated on our side. How do I know the results are converged? That's the next question. Okay, so on ColdStream, it only changes the status of the case to finished if it's satisfied, in the sense that the convergence, there is certain convergence criteria that is to be met, and only when this convergence criteria is met will the results be available, and you will have a finished case. So it is all automated. You will have, there is a certain convergence criteria built in for ColdStream. All right, the next question. What happens if the mesh crashes, or if there's any other crash during the solution of my case? Um, so it is normal for such a thing to happen. We are prepared to deal with crashes and incidents when our case is running. So typically, what happens is if something crashes, there is internal fixes, and we have our R&D department always on the go to solve such issues. They have automated crash crash resolutions and resolving crashes and incidents. But at the same time, if you, for example, set up like a really infeasible or non-physical setup, we've also built in the software uh, for it to let you know that this is the case has crashed, because this is not possible as well. So there are two kinds of crashes and incidents that we deal with, and solvable crashes, there are automated sections on the software itself that are taken care of automatically by the software. If it goes to a point where it's not solvable, then we still have the R&D. It's a direct issue that's raised, and R&D will solve the issue and have the fix back on the software. On the other hand, if you set up something non-physical, then that will give you a message, an error message as well. All right, next question. Are the results validated? Yes, the results are validated. All our cases are usually validated on some standard CFD cases, and a design case is always validated, and the design is extracted uh, by by the software to run a simulation. So this is quite an iterative process, and we do validate these cases against standard CFD cases. So yes, the results are validated. I'm going to take a look at the next question. Uh, okay, how to get access to the software. This is quite easy. If you want to do a trial or if you want just access to the software to take a look at how things are going and things like that, you can you can reach out to us via our contact details. You can also use the website to request access to the platform, and we will get back to you and we'll set you up with the platform so you can have a go at it as well. So that is quite a simple procedure, and you can set it up on your own. All right. I don't think there are any other questions because I don't. Oh, yeah. How does manufacturing affect the design? The manufacturing settings are quite important. They do influence the design to a certain extent. Uh, so when you choose something like, for example, 3D printing, you are expecting more three-dimensional shapes and three-dimensional characteristics to your channels. But when you choose something like CNC, what you're expecting is more 2D designs. So the choice of your manufacturing settings, the minimum feature size, they will play a role in how the design looks, or how the design is shaped, because that is quite a valuable constraint that needs to be looked at in a conceptual or even at the beginning stages of the optimization. The focus is, of course, on the thermal optimization, but there is at a certain point that it optimizes to make sure the design is completely manufacturable. But at the same time, the if the optimizer starts with only three-dimensional channels in the beginning, it cannot at the end resolve and give you only 2D channels, which is why the manufacturing settings are very important. They are taken into account in how the channels are shaped from the beginning itself to meet your manufacturing constraints. So it's definitely an important role that manufacturing settings play in the case setup. I think those that's all the questions. No, I do see a few more, but I don't think we have more time for them. But what I will do is I will reach out to you personally and I will answer your questions. So if you have any other questions or want to know something that I did not cover in this webinar, please feel free to reach out to me. You can also reach out to us on via our website. I will get back to you as soon as possible and answer all your questions. Thank you for joining me at this webinar. I hope everything was clear and you found this interesting. Until the next webinar then, thank you.